Okay, welcome to lecture 14, Engineering Metallurgy, Mechanical Engineering BSc program. Today we are going to talk about iron-iron carbide equilibrium diagram and how various iron alloys are produced. That can be learned from today's lecture. So hopefully you will enjoy the class today, because the steel or iron is the most common material used in the construction industries. So for iron-iron carbide diagram, before we go to that, let's clear a few things about iron. It is an almost pure iron is usually called ingot iron, which have a chemical composition of carbon is 0.012%, and there are some other elements too, like manganese, phosphorus, sulfur, silicon, etc. But very small amount. If you see, it's like 0.017%, which is very small, and that is why it's called pure iron. And there is nothing actually 100% pure. There are always some impurities. So these are the impurities present in the iron. So if the chemical composition of iron is like that, that means the percentage of these elements are like very small, then you can say that is pure iron. And the typical mechanical property, if we talk about for pure iron, its tensile strength is 40,000 psi, and elongation in 2 inch. During the tension test, if the gauge length is 2 inch, then the elongation is found to be 40%, and hardness, local hardness number is in the B scale, number is 30. This is the mechanical property of pure iron. So you need to know that, because in the later slides, you will be seeing that how the mechanical properties of pure iron can be modified using various processes. And as you know, at the beginning of the phase diagram lecture, we talked about allotropic material, which actually shows different crystal structure or unit cells at different temperature, and if they are reversible, then we call them allotropic metal. And iron actually melts at a very high temperature, like 2800 degree Fahrenheit. More than 2800 degree Fahrenheit, iron actually completely melts and becomes liquid. And at 2802 degree Fahrenheit temperature, iron converts into delta iron, which have a which is a solid, 100% solid, and the conversion occurs at a constant temperature. This line indicates that constant temperature, and the delta iron consists of body-centered cubic structure in its crystals. And once the delta iron is completely produced, then temperature starts to drop again, and at temperature 2554 degree Fahrenheit, it actually converts into gamma iron. That means the crystal structure has been changed to BCC structure. And also the property of this iron is actually non-magnetic. That means the gamma irons are have non-magnetic property. And once the conversion is complete at this point, then the temperature starts to drop again. And at temperature 1666 degree Fahrenheit, that gamma iron face-centered cubic structure transformed into body-centered cubic structure again, which is called alpha iron. And this alpha iron is still non-magnetic. But when the temperature again drops to 414 degree Fahrenheit, that BCC structure gets more stabilized, and solid state diffusion occurs. And because of that solid state diffusion, the iron shows the magnetic property. It is still the alpha iron, but it is magnetic now. So if the temperature of iron is more than 1666 degree Fahrenheit, then the iron is actually 1414 degrees Fahrenheit, then the iron is actually non-magnetic. Above that temperature and below that temperature, iron is magnetic, and the BCC structure remains at the room temperature. And all these things happens if you maintain the temperature, the cooling rate very slow. Okay, that means the cooling rate has to be very slow to maintain the equilibrium and to obtain this graph, this type of cooling curve. Okay, any question in here?
Sir, is delta non-magnetic or magnetic?
Delta is also
Delta.
non-magnetic. It's not. It's also the above temperature 1414 degree Fahrenheit. Everything is not magnetic.
Yes, sir.
All right. So this is our iron carbide diagram, in which it is basically a diagram of iron and carbon. Okay. At this region, it is 100% iron. That means pure iron. And on the other side, it was supposed to be 100% carbon. Okay. But most of the material has the iron material that is available, like steel or cast iron, everything actually falls below this Fe3C, that means 6.67%, less than 6.67%. And as we know that when the carbon content in iron is 6.67%, then it forms a compound. This is called iron carbide. Okay. And this iron carbide, since it is a compound, it actually acts like a pure metal. And in the phase diagram, we have studied that the intermediate compound or the compound alloys actually act as a pure metal, and they are represented in a phase diagram as a vertical line. So this DK, this vertical line at 6.67% concentration of carbon is indicating uh, an intermediate alloy. Okay, and this diagram actually continues on the other side. Okay, this diagram actually continues on the other side in a different way, but that is not our concern, because most of the material that we treat lies the percentage of carbon lies within 6.67%. So this is the most important part of iron alloys. So this is what we are going to study in here. So this diagram actually consists of several regions. One of them is the delta region. If we look at this region is the delta region. And before going to that, let's clear the diagram first. Which region is what? We need to understand that. So on the top line, if we consider this top line, if this region up to the eutectic point, and then it goes like that. This region is the liquid region. Above this, these lines, the alloys that have the various carbon content between 6.67% is 100% liquid, and above this temperature, the pure iron is also 100% liquid in this region. And below that, and if you want to find out the Solidus line, in this case, if you want to find out the Solidus line, then this is the Solidus line in here. Let me take a different color. To find out the Solidus line, this is actually the Solidus line in here. Okay. That means Solidus line, finding the Solidus line is not very difficult. It is just, it will connect 2 points between 2 elements, like pure iron, it is connected in this point, and in the case of iron carbide, it is connected in here. And below this line, everything should be solid. Okay, so this is the Solidus line, and the red one is the liquidus line. And there are some regions, very many two-phase regions actually. This is the two-phase region of gamma iron and liquid, and this is the two-phase region of liquid and iron carbide, and this is the single-phase region, the gamma iron in here, this region is a single phase region. Okay, and there is another single phase region that is delta iron, that contains delta iron. We'll expand this view and then we'll discuss this delta region. Okay, and there are also another two phase region, two solid phases in here. This region is contains delta and gamma iron. This is also a two phase region, and another two phase region is in here, which is below the eutectic temperature, gamma and iron carbide. That means it will be a mixture of gamma iron and iron carbide in here. And below the eutectoid temperature line, there is also a two phase region which contains alpha iron and iron carbide. But at room temperature, it will eventually become the pure iron with iron carbide. And another two phase region in here is consists of gamma iron and alpha iron. Okay, that is FG is in this region. And there is another region is called indicating the solubility of iron, solubility of carbon in iron, that is alpha. Okay, and this is called the alpha region. It's a single phase region. Okay, so these are the regions, and there are some reactions that take place in these regions. One of them is the eutectic reaction at point E, and at point J there will be eutectoid reaction. That means two solids will produce a different solid. Okay, so that is also called a eutectoid reaction. And then here is another reaction. Any horizontal line in the phase diagram actually indicates a reaction. That means since this is also a horizontal line, this also indicates a reaction, that is Eutectic reaction. Okay, liquid and solid produces a different solid. Okay, that's the reactions that take place in the iron carbide diagram. And in the case of 6.67% iron carbide, the iron carbide actually melts at this temperature and then becomes completely solidified, and then it remains the same up to the room temperature. Okay. Okay. Any question? All right. Let's move to the discussion. Actually, this is just identification of various phases or various regions, and then we'll go to discuss the various regions. We'll begin with the delta region. So this is the delta region where iron actually, molten iron actually converts into delta iron. It produces delta iron in this region. So if we talk about a pure metal, that is pure iron, then it melts at 2802 degree Fahrenheit temperature, and at this temperature it starts to solidify, and once the solidification is complete, it actually forms delta iron. So from point A to point N, for the pure iron, it is actually delta iron. Okay. And below that N, it actually forms austenite. That means gamma iron. Austenite is actually gamma iron. Okay. And if we increase the carbon content in here, okay, just want to bring them up. Okay. When the if you increase the carbon content in the iron, then let's say if we consider a carbon content like this. Okay, this vertical line actually indicates a certain amount of carbon present in there. So at high temperature it will be liquid, and then when temperature comes to the liquidous line, then solidification starts and gamma iron will start to be produced. So at this point there will be very small amount of gamma iron, and then when the temperature drops like point in here, then gamma iron will start to increase, the solid content will start to increase, and below when the temperature reaches at this point, then the 100% delta iron has been produced. So there will be 100% delta iron which contains the same amount. Let's say if it is 0.02% carbon is present in here, So the delta iron that is produced will have 0.02% carbon. And when the temperature drops below this intersection point, then delta iron starts to convert into austenite or gamma iron. Okay, austenite or gamma iron starts to produce in here. So it is a two-phase region. That means in this region, when the temperature drops at this temperature, then there will be certain amount of austenite and certain amount of delta iron. And those percentages can be found using the tie lines. If you draw the tie lines at a certain temperature, then you will be able to find out how much austenite is produced and how much delta iron is remaining. And when the temperature drops below this line, below this point, then 100% austenite is produced. And that austenite will have the same composition as the alloy, and that is 0.02% carbon will be present in the austenite. Only change that has occurred from this point to this point is the transferring body-centered cubic structure to face-centered cubic structure. Okay, that is the only change that has occurred between these 2 points. Okay, and there will be 100% austenite with composition 0.02% carbon. Okay, any question? Okay, so how the percentage of carbon influences the formation of alloys? If we want to discuss that in this case, so for this alloy, for example, when the carbon content has become 0.02%, then the changes that has occurred is first, so starting point of solidification has been decreased. Okay, initially the pure iron starts to solidify at 2802 degree Fahrenheit at this point, but when 0.02 certain amount of carbon is present in the iron, then the starting point of solidification has been changed. As well as this line actually indicates the solubility of carbon in the at various temperatures. So according to these lines, we have already discussed that in the type 2 phase diagram. So a type 1 phase diagram. So it is not that important. But when if you look at this point, this temperature and this temperature, that means when iron is pure, then the conversion of delta iron starts at temperature 2554 degree Fahrenheit. But when you add the carbon, certain amount of carbon in the iron, then the temperature has been increased. That means at higher temperature, the conversion starts to occur from delta to gamma at a higher temperature. Okay, that is the effect of carbon content in the iron. Okay, in the delta region. Okay, so that's how when you add the carbon, more carbon is added in the iron, then the temperature starts to increase up to this temperature. Okay, where delta iron has reached its maximum solubility of carbon. That means delta iron can have maximum amount of carbon is 0.1% carbon that delta iron can have in its structure, but the temperature has to be 2720 degree Fahrenheit. That means when the temperature drops, delta iron has less capability to hold carbon atoms in its structure. Okay. That means when the temperature drops, more and more temperature drops, more and more carbon gets out of the structure, and the structure actually changes to the conversion of delta iron into face-centered cubic starts to occur. So that is how it changes. Okay, and now that is so the maximum solubility of carbon in the iron structure is 0.1% carbon. Okay, in the delta iron. Now, if we consider a different alloy now, okay, do you have any question for this alloy? If not, then I can move to the next one. Okay, so if we draw another vertical line, that means 0.14%, let's say 13 or 0.14% carbon. If you consider 0.14% carbon, then at this temperature, delta starts to form, and when the temperature reaches at this point, MB line MPB line actually represents a peritectic reaction. Okay, that means a certain amount of delta ion will be produced at this temperature, and then the rest of the liquid will have a composition of peritectic composition, which is 0.18% carbon will remain in the liquid, and that liquid will convert into austenite. Okay, so that means liquid and delta, and that because since the peritectic reaction is about liquid and solid, produce a third solid, so delta will also be involved. Okay, that means at the peritectic temperature line, there will be certain amount of delta plus liquid, and a portion of delta, and so let's say delta 1, a portion of delta and all the liquid will react to form a different solid, which is gamma. The gamma is the austenite. So at this temperature, at peritectic temperature, delta and liquid will react at a constant temperature to form austenite. That means just before this peritectic temperature line, there was delta and liquid, and after the peritectic temperature line, in this region, there will be gamma plus delta. Okay. And when the gamma and delta are produced after the peritectic reaction, when the temperature drops, more and more gamma is produced from delta. Delta is converted into gamma, and below this temperature, there will be 100% gamma. That will be 100% gamma. And if we consider like 0.18% carbon, like at point P directly, so there will be certain amount of delta produced in this region. There will be liquid present, and all the delta and liquid, everything, all the delta and liquid present before the peritectic reaction will be converted into 100% austenite. Okay. And after the 0.18% carbon concentration, if you consider another alloy in this region, then the same thing happens. That means at this temperature, delta starts to produce, and at this temperature, there will be delta and certain amount of liquid present. And an interesting thing occurs in this region is that when delta and some of the liquid will produce austenite, and there will be some liquid still present in the structure. That means before this peritectic temperature line, there will be delta plus liquid, and after the peritectic reaction, there will be no delta, but there will be gamma plus liquid. That means the delta and a portion of liquid will react to form gamma, and some portion of the liquid will remain the same. Okay, and once when the temperature drops below this line, peritectic temperature line, the liquid will convert into austenite directly. That means percentage of austenite will start to increase, and below this temperature at this region, then you will find the 100% austenite. That's how this delta region actually works. Okay. Okay, any question?
স্যার তার মানে কি যত লাইন লাইনগুলা রাইট সাইডের দিকে যাবে তত হচ্ছে কার্বনের অ্যাবজর্বিং ক্যাপাবিলিটিটা বেড়ে যাবে?
যত রাইট সাইডে যাবে, that means হচ্ছে if you move rightward, that means you are increasing the carbon content. Okay,
Yes, sir.
if you are increasing the carbon content, then it is influencing the structure. Actually, it is not forming any delta anymore. Okay, more and more carbon temperature when drops below the peritectic temperature line, there is austenite. That means the structure has been changed to gamma. That means face-centered cubic. That's what occurring in here. Okay.
Yes, sir.
Did you understand?
Yes, sir.
Okay. So this is how the delta region works. But thing is that this delta region is not a significant region. Studying this delta region does not make any difference in the production of or manufacturing of carbon alloys. That means the iron carbon alloys. Okay, I'll tell you why. So this is okay. There are some other points in here. I have already told you. The line NM represents, that means N and M represents the beginning of change from BCC to FCC for alloy containing less than 0.1% carbon. That's what I said. Like this MN region actually indicates the starting point of transformation from delta to austenite. And portion MP peritectic reaction for alloys between 0.1 to 0.18%, and portion PB will be like peritectic reaction, same peritectic reaction, 0.18% to 0.5% carbon. Okay, these are the same thing. Delta solid solution, and allotropic change is completely bypassed for alloys containing more than 0.5% carbon. If you add more than 0.5% carbon, then this region does not have any significance. That means this region will not be of significance. That means there will be no production of delta. Up to this 0.5% carbon, there will be some amount of delta produced and then converted into austenite. But if the carbon content is more than 0.5%, then there is no production of delta iron. However, that's what I said, no commercial heat treatment is done in the delta region, therefore not so important. Why this is not done? Because this is delta region is at very high temperature, like 2500 degree Fahrenheit to 2800 degree Fahrenheit. If you cool the steel at this region, let's say at 2720 degree Fahrenheit temperature, you raise the temperature of iron at 2720 degree Fahrenheit, and then you cool it very fast. Whatever faster cooling you apply does not matter, because delta iron eventually will convert into austenite. So above this region temperature 2554 degree Fahrenheit, whatever you do, heat treating above this temperature does not actually change the structure at room temperature, whatever cooling rate you apply. Okay, so during the heat treatment, you will not get this delta structure at room temperature. The main purpose of sudden cooling or fast cooling of any alloy is that to retain a certain structure. But if you want to retain the delta structure, it is not possible, because whatever cooling rate you apply, it eventually converts into austenite. Okay, so there is no heat treatment is done at that temperature. It is just waste of energy and time. Okay, that is why this region is not so significant. Okay, any question? Right. So
austenite হইলে স্যার austenite হইলে প্রবলেমটা কি স্যার?
There is no problem. There is no problem. If it is converted into austenite is face-centered cubic structure. Okay, it is not delta. So most of the heat treatment is done after production of austenite, because if you you can retain the structure of austenite when you apply a very fast cooling, but you cannot retain the delta structure. So that is why it is not significant. The delta region is not significant. That is the region. Okay, and the converting to austenite, it does not have any problem. Okay.
Yes, sir.
Okay, so here I discussed all of these. Okay, no, it's not. So just to make some more parameters or more terminology used in the iron carbide diagram. I have already talked about austenite and iron carbide. Iron carbide is also called cementite. Okay, iron carbide is also called cementite. So these are the regions actually: liquid and austenite, liquid and cementite, austenite, 100% austenite, and then when after the eutectic reaction, the product that is formed at this temperature is called lead-burite. Okay, yeah, after the eutectic reaction, and after and in this region there will be austenite plus cementite, the mixture of austenite and cementite, and here the alpha iron is also called ferrite, and the region in here, that means this region actually indicates the mixture of ferrite and austenite will stay in this region. It's a two-phase region of ferrite and austenite. And after the eutectoid reaction, the product that is formed, or that means the microstructure that is formed, is called pearlite. Okay, it's called pearlite, which is a mixture of ferrite and cementite. Okay? That means the iron carbide and alpha iron, it is a mixture of that. And when the carbon content in the iron is up to 2%, we call them steel. And if the carbon content is more than 2%, then we call them cast iron. Okay, and above that, that's a different thing. Okay, that is also cast iron, but it's kind of different. You'll learn about that in the other part of metallurgy, that is part B. Again, and this steel and cast iron can also be divided into two parts. The first part is called the hypoeutectoid steel. The steel which contains 0 to 0.8% carbon is called hypoeutectoid steel, and the steel that has 0.8% to 2% carbon is called hypereutectoid steel. And in the case of carbon cast iron, it is the same. The hypoeutectic cast iron, in this case it is eutectoid, and in this case since it involves the eutectic reaction, it is called hypoeutectic cast iron, and it is hypereutectic cast iron. The range is like 2 to 4.3% carbon is hypoeutectic cast iron, and 4.3 to 6.67% is called hypereutectic cast iron. Okay, now to understand the iron carbide diagram more clearly, what we will do is that what we are going to study we're going to study various steels. Okay, various steels that is formed in here. Like for example, if we consider a steel at this point, another steel at this point, another steel. Okay, so various percentage of steels, how the microstructural evolution occur, and how you can modify the properties. We will be studying that in the next slides. And that is called the slow cooling of steel. Okay. If we raise the temperature of a steel at very high temperature and then slowly cool down, then we'll get what we're going to get is we're going to study that. As we have already studied 0.2% carbon in the delta region, 0.02% carbon in the delta region, and eventually it forms austenite. So we are not moving up to the delta region. We'll start the cooling. We will hit the steel 0.2% carbon steel in the austenite region, and then we'll do the slow cooling to see how microstructural evolution occur. Okay. So at this temperature in here, okay, at this temperature, this is 100% austenite. This is the austenite region, and there will be 100% austenite. All the grains will have 100% austenite. Okay. And then when the temperature comes below this GJ line, okay, then austenite starts to transform into ferrite. That means there will be some ferrite produced around the austenite grains. Okay, that means these grains are pro-eutectoid ferrite. Ferrite starts to produce. As the temperature drops and just above is a line, that means just above the eutectoid temperature line, there will still be some austenite grains, but small amount of austenite grains. These are the austenite grains in here, and most of them will be ferrite. And then that austenite, when the eutectoid reaction takes place, that austenite actually converts into ferrite and iron carbide, and which is called pearlite. And how this conversion occurs, if we go to the percentage, it's also in here. Just above AJ line, there is 25% austenite and 75% ferrite is produced, and with 0.8% carbon. That means the austenite will have, there will be 25% austenite with 0.8% carbon in it. And since the 0.8% carbon indicates the composition of this composition, that means the eutectoid composition, so eutectoid reaction will take place. And just below the AZ line, there is 25% pearlite. That means the 25% austenite has been converted into pearlite. Pearlite is a mixture of ferrite and iron carbide. And how this pearlite forms? Pearlite forms like similar way as the eutectic mixture. The way eutectic mixture is formed, pearlite is also formed like this. For example, in a grain of austenite, if we consider this is a grain of austenite, at some point cementite starts to form. The black region is the cementite, and on the both side of cementite, ferrite starts to accumulate, and this propagates throughout the grain, this way and this way. This propagates, and that is how you get a mixture of ferrite and cementite. Cementite is iron carbide and ferrite is alpha. This is alpha and this is iron Fe3C, iron carbide. Okay, so this is the mixture. The pearlite is the mixture of ferrite and cementite, and that's what produced from the austenite. So in the case when you consider another alloy at this region, so there will be more and more pearlite. More austenite will be remaining in the structure, and more pearlite will be produced. That means if you move from this point to that up to 0.8%, so the amount of ferrite will reduce and amount of pearlite will increase. And at this temperature, at 0.8% carbon, there will be 100% pearlite. That means there will be the microstructure will be 100% pearlite or 100% mixture of ferrite and cementite. Okay, any question?
Sir, যে পয়েন্টের কি যে পয়েন্টের উপরের সাইডে যখন থাকবে তখন অস্টেনাইট কিছু পার্সেন্ট থাকবে, আবার ফেরাইট প্লাস অস্টেনাইট কিছু পার্সেন্ট থাকবে, আবার সিমেন্টাইট কিছু পার্সেন্ট থাকবে, এরকম কি?
না, এখানে if you want more clarification, that is like just above this temperature line, okay, just above this temperature line, there will be ferrite grains, right? Ferrite grains are produced and some of the austenites will be present. Okay.
Yes,
and
sir.
just after the eutectoid reaction, this all the remaining austenite grains will be converted into pearlite. That means there was a austenite grain that has been converted into pearlite. There was another austenite grain that has been converted into pearlite, and the ferrite that has been produced before the eutectoid reaction, that will remain the same. The only change will only occur in the austenite grains. Did you get my point?
Yes, sir.
And after when the temperature drops, it actually remains the same. Okay.
Yes, sir.
Okay, do you need more clarification? I think your voice is kind of low. That means you did not understand clearly. Am I right?
No, sir, I asked about point J.
Or you asked about point J.
Yes.
So in the case of point J, there is 100% austenite, right?
Yes, sir.
Above the temperature, there is above the eutectoid reaction, there is 100% austenite. So all the grains are austenite. Okay. And after the eutectoid reaction, so all the grains will be converted into perlite.
Yes, sir.
Get it?
Yes, sir.
Okay. So these are some microstructures.
স্যার ওইখানে স্যার 25% যে ওইটা কিভাবে আসছে স্যার? ওটা কি দেওয়া ছিল নাকি স্যার?
This 25%.
25% অস্টেনাইট স্যার। জি স্যার, এটা
Now we need to go back to lecture 2 on phase diagram, right? So to find out 25%, how to, it's not given. You can find it out. If you draw a tie line in here, this is our alloy, right? And this point indicates 0.1% carbon, let's say 0.1% carbon. Okay. So this point indicates 0.88% carbon. So how much, so the ferrite that has been produced will have 0.1% carbon chemical composition, and the austenite that has been formed will have, that is remaining will have a chemical composition of 0.8% carbon. If you want to find out how much austenite is in there, then what should you do? We need to apply the lever rule, right? So if we say this is point H, this is point J, and if we say this point is K, okay. So to find out the percentage of austenite, we need to we need to have Hj below and to find and Hk at the top. So that's how you get the percentage. That means there will be 0.1 divided by 0.1 divided by 0.6. So this will give you the 25% austenite. Did you understand?
Yes, sir.
Okay. In the phase diagram, that's why I told you, like, you have to attend the classes for phase diagram. Otherwise, you'll not understand. Because for all the cases, if I want to describe this, how to calculate the percentage of each phases for all the cases, it's gonna take a very long time to finish the lectures. Okay, that is why you need to know the theory first, and then you'll understand it very easily. Okay. So I think okay, go ahead.
প্যারালাইটটা স্যার ওই ইউটক্টেড মিক্সার, এটা মানে কোন দুটো সলিডের মিক্সার আর কি?
Perlite is the mixture of ferrite and cementite. Okay? Ferrite and cementite. This is the mixture of ferrite and cementite. Okay?
Yes, sir.
It's in here. Okay. This is how the perlite formation occurs, and it is a mixture of ferrite and cementite. Okay. Any more question? Okay, so this is some there's some example of slow cooling of 0.2% carbon steel. This is the real life image of microstructural image of 0.2% carbon steel. In this case, at 100% magnification, 100x magnification, there is 25% perlite at 100x magnification, and if you increase the magnification up to 500x, so there will be some, the white regions are indicating ferrite, and the black regions in here is indicating perlite. Okay, so the perlite percentage is 25% and 75% will be ferrite. And for more magnification, these white regions are still ferrite, and the black regions are the combination of ferrite and cementite. That's how you can see that, like the appearance of white color in the microstructure. Okay, and for 0.4% carbon at 100x magnification, there is 50% perlite, and so there will be more black regions will appear in the microstructure. And then for 0.8% carbon at 500x magnification, you'll see like perlitic structure. That means all of them are perlite. Okay, so these white regions are also perlite. As you see, there are a small amount of iron carbide is present in this region. So the whole microstructure at 0.8% carbon will give you the 100% perlite. So now the question is, how do we do the heat treatment? Okay. Why do we do the heat treatment? That's the question. So if you want to do the heat treatment, that's the main purpose, is to retain some structure. Okay. And to do that, you can convert, you can do the slow cooling up to, let's say, this temperature. You do the slow cooling, there will be certain amount of ferrite produced, and rest of them will be the austenite. And then you suddenly cool it down. Suddenly apply fast cooling. Then what will happen is that the austenite structure will retain. Okay, and the structure, final microstructure will contain ferrite and austenite instead of ferrite and perlite. Okay, so the ferrite has a different mechanical property, austenite has different mechanical property, and combination of ferrite and perlite, which is ferrite and cementite, which is called perlite, it will have a different mechanical property. So whenever you change the amount of ferrite or amount of austenite or amount of perlite, then you will have a different mechanical property. That's how you can modify the mechanical property of a single alloy. You can have a wide range of mechanical properties depending on cooling rate and how you apply the cooling. Okay. So what happens after 0.8% carbon? So if you consider alloy 2, there is 100% austenite. All the grains will have austenite. And when the temperature comes below this line, that means CJ line, okay, then on the boundary of austenite, cementite starts to produce. Okay, cementite will start to produce. And as the temperature drops, more and more cementite network will be produced. More and more cementite will be produced, and there will still there will be some austenite present. Okay, just above the eutectoid temperature line. And when the eutectoid reaction is taken place, then all the austenite has been converted into perlite, and cementite network will be the same. That means when as you move on the right side, more and more cementite will be produced. Okay. If you move on this direction, that means if you increase the carbon content, more and more cementite will be produced. Okay, and less amount of perlite will be seen. And 100% perlite can only be seen in the case of 0.8% carbon. Okay. And this is one of the example for 1% carbon. 1% carbon steel. In this case, at 500x magnification, these are the cementite networks. Okay, these black regions are the cementite networks around it, and 1.2% carbon. These are basically the cementite networks. Okay, these are basically cementite networks, and 1.2% carbon, 300x magnification. The cementite network appears as white region, and then the gray, the perlite actually appears as a combination of cementite and perlite. Okay, that's how we distinguish between the grains or crystal structure. Okay, any question? All right, then This is a comparison table, like effect of carbon content on mechanical properties of steel. Like if you increase the carbon content of on the steel, like 0.0 to 1.5% in the case of steel, then you'll see that in the case of tensile mineral hardness, when with the increase of carbon content, mineral hardness increases sharply, rapidly, almost linearly. Okay. And if you also the tensile strength increases, but at some point tensile strength does not increase anymore. That means if when the carbon content is more than 1%, the tensile strength becomes saturated. The tensile strength does not increase anymore. Up to 0.1% carbon, tensile strength increases. At the same time, yield strength shows the similar behavior. If you consider the yield strength, it also shows the similar behavior. At 1%, up to 1% carbon, it increases, but above 1% carbon, there is no change in the yield strength in the case of tension test. And these are the tension properties are also related to the reduction of area and elongation. The elongation actually decreases. That means more and more carbon is added in the iron, it becomes brittle. Okay, that means the elongation is very small. The brittle structure does not show much elongation, and at the same time, reduction of area is also very small. Okay, so and in terms of impact energy, that means Charpy impact, the more and more when you decrease the so increase the carbon content, the Charpy impact decreases sharply. That means since the structure has become brittle, so Charpy impact shows less amount of energy absorption with the increase of carbon. Okay, so these are the effect of carbon content in the mechanical properties of steel. How the mechanical property changes with the increase of carbon content in the iron. So now the heat treatment. Let's move to the heat treatment. If you do not have any question in the previous slide, do you have any question in here? Okay, so we'll move to the next slide. That means we'll start the heat treatment. The heat treatment is basically, there are some objectives. That means why we should do the heat treatment. To relieve stresses set up in the material after hot and cold working to improve machining. That means, as you know, the hot working and cold working processes involves hot rolling, hot forging. There are many different cold rolling, cold forging actions. Because of that, there are internal stresses developed, as we have studied in ME3215. And to relieve those internal stresses, we need to do the heat treatment to improve the machining. Because when you do those kind of mechanical treatment on the material, they become very hard in some regions, and it is very difficult to cut or do the machining. So you need to relieve this internal stress in the crystals, and then you need to do the machining. So it is a very important task for machining. And also to improve the mechanical properties, tensile strength, hardness, ductility, shock resistance, the mechanical properties can be improved. For example, in the case of iron, if you do it, if you cool it very slowly, then you will have more ductility. And if you cool it very fast, you will have more hardness. Okay, so the tensile strength will be like this. It will also depend on how you apply cooling of a steel. Okay, so you can improve the mechanical properties according to your requirement. And to modify the structure of the material to improve electrical and magnetic properties, the electrical and magnetic properties can also be modified using the heat treatment. And to increase the quality of metal to provide better resistance to heat and wear. To increase the you can also improve the quality of metal for better resistance to heat and corrosion and wear on it, because if you do the surface heat treatment, then you'll be able to reduce the corrosion of the surfaces. To change the grain size has significant effect on machining as well as the mechanical properties of steel. So you can also do this with the help of heat treatment. And to stabilize the structure at elevated temperature, at high temperature, how the metal will behave, you can also control that with the help of heat treatment. And it is a combination. Heat treatment is basically a combination of heating and cooling operation, and also depends on the time, how long or how fast you are doing the cooling, okay, or you are doing the heating. That heating rate does not have much effect, but the cooling rate has significant effect on heat treatment. So a combination of heating and cooling operation, timed and applied to a metal or alloy in solid state in a way that will produce desired properties. That means you can control the cooling, heating or cooling rate and the time to modify the property of a material with the help of heat treatment. And all basic heat treatment of steel involves transformation of or decomposition of austenites. That means this heat treatment on steel, since we are concentrated on heat treatment of steel, the most of the heat treatment is done in the austenite range. That means the heat treatment is done, you have to form the austenite and then you apply the cooling of different rate to find out, to get the desired properties. The nature and appearance of these transformation products determine the physical and mechanical properties of any given steel, as I already discussed that. And the first step of heat treatment of steel is to heat the material to some temperature. At what temperature you want to heat it up, and there are some critical range where you need to form the austenite. You need to form the austenite first, and then you need to do the cooling. And the rate of heating is not significant, as I say, and unless highly stressed material. If the material is very stressed, then rate of heating will have some effect, but if not, then rate of heating does not have any effect on the heat treatment. And as I said about the critical range, at what range you need to heat it up to do the heat treatment, and that can be seen in this diagram. This diagram actually shows for the steel, this is the 0.8% carbon, and all above that like 1.2% carbon. These are the steels, and above that there will be the cast irons. Okay, we're not concentrating on cast iron. We'll only concentrate on steel. So for the steel, the Eutectoid temperature line actually indicates the lower critical temperature for heat treatment. Okay, and and this line here, SC1 line, is actually indicating the upper critical temperature line for heat treatment of steel. Okay, and if you want to do annealing, so annealing range is above this upper critical temperature, 50 to 100 degree above this upper critical temperature line. And normalizing range is more than that. Okay, that means you have to heat it more than that. But interesting thing is in here is that for normalizing, for annealing, you just need to heat it up below above this upper critical temperature line for more than 8.8% carbon. But in the case, if you want to do the normalizing, then the upper critical temperature line is defined by this line. So above 50 to 100 degrees Celsius temperature of this line, you have to heat it up to form 100% austenite. That means for annealing, I'll talk about the annealing and normalizing. For this time, you just remember that for annealing, the heat treatment has to be done above the upper critical temperature line for below 0.8% carbon. For above 0.8% carbon, it is above the lower critical temperature line. But for normalizing, you have to heat it up always above the upper critical temperature lines. So these are the upper critical temperature lines. You have to heat it up more than 100 to 150 degrees above the upper critical temperature line. And for normalizing, the condition is that you have to produce 100% austenite. And as we know, this region is 100% austenite region. So for normalizing, you have to heat it up at normalizing temperature. That means above the upper critical temperature line. Okay, that is what we found out from the iron carbide diagram. Okay. First, let's discuss about the annealing process. For annealing, the process consists of heating of steel to a proper temperature. That means above the upper critical temperature line, and then cooling slowly. Purpose: soften steel, relieve residual stresses, refine the grains. We have already discussed all these things. Improve gas trap in the metal during casting. During casting, there is a possibility of gas trapping, as we said, we saw that blowholes or pinholes present in the casted product, and those can be distributed or removed with the help of annealing. Those gas can be released from the metal. Improve electrical magnetic properties and improve machinability. So these are the purpose for conducting annealing, to mostly soften the steel for machinability, or to increase the ductility, or to relieve the residual stresses. Okay. And since the cooling is very slow, in the case of annealing, as you said, the cooling has to be done very slowly, so you'll get it will resemble the iron-iron carbide diagram. Equilibrium diagram is closest to the iron-iron carbide diagram in the case of annealing. As we said, we saw that in the case of annealing, in the iron-iron carbide diagram, it can be explained using the iron-iron carbide diagram. So there is 100% austenite. During the heating, the part of material will disintegrate and form 100% austenite. And after the annealing, you will get the more distributed structure of ferrite and pearlite. It will be more distributed, and there will be softer product will be produced. Okay. So this can be explained, or how much pearlite will be produced, how much ferrite will be produced, can be explained using this iron-iron carbide diagram. Okay. But in the case of other heat treatment, it is difficult. I'll tell you why it is very difficult in the case of other process, because in the other processes we do not apply slow cooling. Okay, for only in the case of annealing we apply slow cooling, so that we get softer structure, or it resembles the iron-iron carbide diagram, and the amount of constituents can also be found from iron-iron carbide diagram analysis, or using a tie line. Okay. And in the case of full annealing, percentage constituent for hypoeutectoid steel, as the carbon content increases, the pearlite content also increases. That means the mixture of ferrite and cementite increases. And as more carbon content is added, the pearlite decreases, but cementite increases. In this case, ferrite is 100% ferrite is at 0% carbon, and 0% ferrite at 0.8% carbon. That means everything has become pearlite. But above the 0.8% carbon, there is cementite starts to produce, and pearlite amount of pearlite starts to decrease. So this is how you can quantify for various carbon content how much. For example, if you want to find out for 0.5% carbon, how much ferrite is present and how much pearlite is present, that can be found from here. Okay. So this point indicates like this range will give you the percentage of pearlite, and this height will give you the percentage of ferrite. And this is how we can predict the properties of the final material. Okay, since if the pearlite has let's say if the pearlite has a tensile strength of 120 megapascal, let's say for example, and ferrite has a tensile strength of 50 megapascal. Okay, so a material consists of 20%, let's say 0.2%, 2% carbon, like 20% ferrite and 80% pearlite will have like a strength of 0.88. So if you multiply these two, so if you sum up these two, then you will get the property of the combination of ferrite and pearlite in the structure. So that's how we can predict, depending on how much ferrite and how much pearlite is present in the structure, you can predict the final strength of the material. Okay, any question? All right, so the next one is the spironizing. It's a very simple process of obtaining spironized product. The spironizing is the process produces spheroidal or globular form of carbide in a ferrite matrix to improve machinability. That means the carbide that has been produced in the microstructure can be modified. That means the perlite, the carbide, that means iron carbide or cementite particles or cementite grains can be modified to become circular or spherical, okay, to improve the machinability. If the cementite is very hard material, okay, so if we can produce circular cementite, then we don't need to cut it. For example, you have a cementite like this, and you have a cementite like a circle, like this, and there's another cementite in here, and there is another cementite in here. Like, you know, if it is elongated structure, or if it is like spheroidal, then during cutting, if you cut it like using a tool, then you have to break the cementites during the cutting. But in the case of when you produce the cementite like spherical particles, then uh, cutting occurs, let's say, around the cementite particles. Okay, so it takes less effort to cut the structure. That is why the machinability is increased if you do the spheroidizing. That means the main purpose of producing spheroidite is spherical cementite particles. Spheroidizing has the main purpose to convert the elongated grains of iron carbide into circular grains or spherical grains, so that you can cut it very easily. Okay, so spheroidizing can be done by one of the following methods. There are two methods: prolonged holding at a temperature just below the lower critical temperature line. You can hold the structure below the lower critical temperature for a long time. Then you will obtain spheroidal, that means spherical particle of cementite. And second one is heating and cooling alternately between temperature just above and below the lower critical temperature line. Okay, you can also obtain the spheroidized structure using this. And third one is heating to a temperature above lower critical line, and then either cooling very slowly in the furnace or holding at a temperature just below the lower critical temperature line. These three methods can be used to produce the spheroidized structure, which improves the machinability significantly, and also increase the tool life. And prolonged time at elevated temperature completely break up the perlitic structure and cementite network to produce spherical particles. Okay, cementite will become a sphere, which is the geometric shape in greatest equilibrium and its surroundings. As I say, the cemented particle and entire structure may be called spheroidite. Okay, that means you just break up the structure and produce spherical cementite particles, so that you can cut it very easily. And also there are some other properties can be obtained if you do the spheroidizing, like minimum hardness. Hardness will be very small, maximum ductility, maximum machinability. These are the important properties that can be obtained by doing the spheroidizing. But the low carbon steel does not spheroidize because it has very small amount of iron carbide. That means very small amount of cementite present in the low carbon steel. But if the steel is kept too long at a spheroidized annealing temperature, the cementite particles become elongated and reduce machinability. But you have to also take care of the time, how long you want to keep it in the spheroidizing temperature. Because if you keep it for longer time, then the particles will be elongated again, and then it will become, it will not give you the desired property. So the next one is stress relief annealing. It is similar to annealing, only there is a temperature range like 1000 to 200 degree Fahrenheit critical temperature. It has to be carried out, and it is sometimes called subcritical annealing or useful It is basically used for removing the residual stresses due to heavy machining or cold working processes. Let's say you have done cold rolling on some steel sheets, and then you need to remove the residual stresses to do the more hot working process. Then you do the stress relief annealing. You just heat it up to 1000 degree Fahrenheit, keep it for some time, and then cool it slowly so that stresses become relieved. Next one is also similar type of annealing. It is basically used in the sheet or wire industries, usually carried out by heating the steel at a temperature like similar lower critical temperature line, and also it is applied after cold working and softens the steel by recrystallization for further working. Just step by step working, like you do a certain hot working or cold working process, then do the process annealing, and then do it again. Okay, something like that. It is very similar to stress relief annealing. Okay, it's a kind of similar thing, but it is done in a process of manufacturing certain product. That is why it's called process annealing. And I think we cannot continue today. It's do you have 5 more minutes? Can I take 5 more minutes?
Yes, sir.
Yes, sir.
Okay. So for the normalizing of steel is carried out by heating approximately 1000 degree. That's not 100 degree Fahrenheit. That should be 1000. Okay, and above the upper critical temperature line, followed by the cooling in still air at room temperature. That means in the case of normalizing, you heat it up above the upper critical temperature and then just leave it at the room temperature. Okay, then it will be cooled down, and then the structure will be normalized. Process of normalizing to produce harder and stronger steel than full annealing. In the case of full annealing, you will get a structure kind of softer, but in the case of normalizing, since the cooling rate is a bit higher, so you'll get a harder or a stronger steel than full annealing. And it may also be used to improve the machinability, modify or refine dendritic structure and other internal grain structure, etc., and also improve the response in hardening operation. Okay. And iron carbide diagram cannot be used to predict the proportion of ferrite, pearlite, or cementite and pearlites. Okay, that means since the cooling rate is high, you cannot use iron carbide diagram to predict the property. In this case, you have to analyze the microstructure and then you have to calculate the properties. Okay, so you cannot just simply use iron carbide diagram to predict how much ferrite is there, how much pearlite is there. You cannot do that. Okay, you have to look at the microstructure and then quantify. And this is a 0.5% carbon steel with normalizing. In the annealed condition, this steel would have shows 62% pearlite and 38% ferrite. When you do the annealing, the same steel, 0.5% carbon, when you do the annealing, it will have 62% pearlite and 38% ferrite. But due to air cooling, when you do the normalizing, this sample has only 10% ferrite. Okay, the sample will have only 10%. This white regions only 10% ferrite, and all of them are cementite. Okay, it is the cementite network that reduces the strength on annealed hypoeutectoid steels, and normalized steels show an increase in strength because of this modified structure. Okay. So that is why you said like you cannot use the phase diagram or iron carbide diagram to predict how much ferrite is present in there. Okay. And due to faster cooling, the pearlite that has been formed is fine, very small particle size is produced, and ferrite is very soft and cementite is very hard. Since the cementite plates are very close in normalized steel, they offer an increased hardness. That means when the very fine structure means the distribution of ferrite and cementite, since they stay together, let's say I'll show you that structure. Like distribution of ferrite and cementite is very uniform and very fine, and that is why it gives an increased hardness than then normal annealed steel. If the annealed hardness is 10 in the case of Rockwell C scale, the normalized hardness will be 20. It's almost twice. Okay. And how does it occur? It occurs like before, when you do the annealing, then you will have thicker plates of cementite plates and ferrite plates will be thicker. But once the normalizing is done, then the cementite plates and ferrite plates will be thinner. That means more uniform distribution and more finer distribution of ferrite and cementite can be obtained. Okay. And that is why the hardness also increases. Okay. And as cooled from high forging temperature, after forging you get microstructure like this, but when you do the normalizing, then the cementite particles will be more distributed and you will get more uniform structure and more superior properties. Okay. Okay, that's all for today. Like we'll study more heat treatment processes like tempering, hardening, and surface heat treatments will be studied in the next lecture. And please ask if you have any question regarding normalizing.